Hi guys, so here we are to solve one more time. Today I bring you series, and this exercise are taken from the last winter exam GTU, for Math-1 last winter exercise for Math-1. So they are to analyze the convergence of a series. And here I have n squared upon 7n. The second is put the power n factorial square upon 2n factorial, and the third is minus 1 to power n ln of n, and goes to 1 to infinite. So for this exercise, let us solve for this first, second, and third. This is first, second, and third. So let us solve for this one. Here I will use root test. Root test. This can be solved with even by root test or by ratio test. Why root test? Because I have only n, and I have here a power of n. Directly this root can be cancelled, and this one root with index n, and when this the expression inside is n, this will be 1. So this will be easy to me to solve by root test, but I can also solve by ratio test. See here, by root test, limit when n goes to infinite. What will I do? The first thing here I just have to write and consider is what is un for the first exercise. Un is n squared upon 7 to the power n. So it's this one is un. Put here un, n squared and 7 to the power n here, in the exponent 1 upon n, by root test. So what we have here, we have just to solve. N goes to infinite, and here I will get n upon 1 by n, or raised to 1 by n, 2 out. And here I will get also 7 raised to n time 1 by n. Now here, what will I get? I will get this, this exercise like this one, in this way. Limit of root n, and here this is square, and here I'll get only 7 down. Now what is limit of root n with index n goes to infinite? 1 bunches. What is this limit? This limit is equal to 1. Why? Very simple. This is a consequence of this limit also. Limit of ln upon n when n goes to infinite is equal to infinite by infinite. Nice? This limit can be converted into this 0 upon 0. Why? Very simple. Just this can be arranged in this way: 1 upon n by 1 upon ln. So in this way you'll get 0 on 0. So if a limit accepts this indetermination, so we can just use L'Hospital rule for this one. So if they accept, this is the same of this. So if this accept this indetermination, so we can apply L'Hospital rule directly to this one. So then by L'Hospital rule, we have to derive the first and the second one. Deriving this one will be 1. Deriving this one, 1 upon n. If we just substitute 1 upon n here, 1 upon 0, 1 upon infinite. 1 upon infinite, it will be 0. 1 upon infinite upon 1. This will be 0. So if this limit is 0, so what can I say? What can I say about if this limit is 0? Now, what is the conclusion that we take about this limit? Root of n okay, and n. This is all square. Don't worry about the square, about this one. Okay, so the next step, okay, the next step, it is just to do what we know. Okay, forget about this square. Okay, just use this one. This is limit of n 1 by n. So this limit can be Euler to the power ln of n 1 by n. This 1 by n come here. Okay, this will be Euler 1 by n, and here down you got L of n. Okay, and this limit is here, infinite. So then you get Euler to the power ln by n. This is the limit. This is infinite. So this limit we have already proved. This is what this limit is here. Okay, and this is equal to 0. Put here 0. Euler to the power 0. It is equal to 1. That's why I told you that this limit, it is true, and this is a consequence of this one. Now just substitute in here. What you get? You get 1 upon 7. This is 1 square upon 7. 1 square upon 1 square upon 7. It is 1 upon 7, less than 1. So by root test, it is convergent. Okay. Now you can also calculate this one by ratio test directly. You will solve this one. Yeah, the most common one, it is by using ratio test. Okay. If you are using root test, just be sure about this limit here. Okay, so okay, now let us go for the next exercise. The next exercise, it say that we have this series to the power n factorial square upon 2n factorial. So here we are going to solve. We have to apply, okay, apply ratio test. Why ratio test? Because we have polynomial, polynomial in factorial, and we have also power. So apply ratio test. This one here, okay, here un, it is to the power n factorial square upon 2n factorial. But un plus 1 will be 2n plus 1. Then here you get n plus 1 factorial square upon 2n, okay, 2n plus 1, okay, all of this is factorial. Now just apply for the limit. This is equal to this one. So what we have to know about limit for ratio test, un plus 1 upon un must be equal to L. Okay, so L, okay, if L is less than 1, this is, we can say that the series will converge. Okay, the series will converge. If L is more than 1, series will diverge. And if L is equal to 1, test fail. Okay, test fails. So now let us just solve this one. N goes to infinite, and what we are going to do this one, just put this one and un plus 1 here, okay, to the power n plus 1, then n plus 1, okay, factorial, it is square, upon 2n plus 1 factorial, all of them. Then it will be multiplied by the inverse by the second time, because we cannot divide fraction. We just remain the first and multiply by the second inversely done. So just invert this un, it will be 2n factorial upon 2 to the power n, and here n factorial square. Okay, now what we have to do, some simplification. This limit n goes to infinite. Here it will be 2 to the power n times 2. Okay, and here whenever you have this one, it will be n plus 1, then n plus 1 minus 1, then it will be n factorial. It is all square and squared. Okay, all upon, and here you will get the same. But here, if you see well, it will be this 2n plus 1, okay, this one minus 1. Okay, so first I will just repeat this one as it is, then I will have to multiply by 2n plus 1 minus 1. This will be 2n plus 1. Okay, I have to end with this one as this one, so then I have to apply again factorial. It will be 2n plus 1 times 2n plus 1 minus 1. Now it will be 2n, then 2n factorial. Okay, so this will be this guy times this one, then times this one. So it will be expressed like this one: 2n plus 1 times 2n plus 1 here, and then times 2n factorial. Okay, time. Now second part, I have just to do this one. This is the same, just keep it as it is, the same. And here 2 to the power n, and here n factorial square. Now see, simplification will go on. This and this, this and this, this and this. What will I get? This one, and infinite. This is 2 and square, and so on. Here I will get 2, okay, n plus 1 square upon 2n plus 1, and here 2n plus 1. Okay, can you see this one? This can be simplified by this. Okay, yeah, or instead you can just directly pick up the greatest common n here, n with the greater degree here, and then with the greater degree here, just divide them all and you are done. But okay, here you get 2n plus 1, and here downstairs you will be 2 and 2n plus 1. Okay, this limit will be equal only to 2n upon 4n. Okay, n. This limit will be equal 1 by 2. 1 by 2 is less than 1, so we can say by, okay, we can say 1 by 2 is less than 1. We can say that by ratio test. Okay, ratio test, this is what it is, convergent. Okay, now the last exercise that we are going to do this here, it is this one. I don't know if you remember this one. This is the third. This is a easy one. Okay, for 1 minus 1 raised to n, and here ln of n. Okay, whenever we have an alternative series like this one, so the best option for us is to apply Leibniz test. Okay, let me just go here, Leibniz test. Why? Because we have here an alternative series. What did it say? It says that first it has to have, okay, it must be, okay, how can I say, the absolute value of the function, not function, of the series, the absolute value of the series. What is the absolute value of the series? un, okay, without this negative, just pick up 1 here, okay, that is 1 upon ln, the absolute value of the series, okay, must be a decreasing series, okay, must be decreasing. I mean, un plus 1, okay, must be less than un. It's okay, just like this one. And if you check this one, you will see that this directly is true. Okay, let us solve for this one. So we just put here 1 upon ln plus 1. Okay, let us see if this is true by 1 upon ln. Okay, just check this equality and see if this is true or not. Okay, if you see this one, just solve for this one. This guy come here and this guy come here, just invert. If I invert minus 1, I will invert also the equality here, so I will get ln plus 1. Okay, ln plus 1, and here I will get l of n. So here it is proved. We can see that l of n will be always less than this guy. Okay, this is for un, this is for un, this is for this one. But anyway, just substitute for value if you are in doubt. Substitute for value directly, put as u1, check for u1, when this here is 1, when this here is 2, and so on. Just check and you will see this one. Okay, so just check for this one. What is u2? u2 put here, n2 will be 1 upon ln of 2. Okay, will be less than ln of 1. Just check. Okay, check if this is true, whether it's true or not. But here, suppose here we have this one here, we'll just to do what? Okay, I will just prove this one directly, this and this. Okay, so it is Euler to the power ln. Okay, if I put a Euler here, ln plus 1, and here also Euler to the power the same, it will be ln and n. Here it will be n plus 1. Okay, greater, then here it will be n. So in this way it is proved that un, okay, sorry, un will be always n plus 1. Un, it's un plus 1, sorry, un plus 1. Okay, in this way you can just check that whatever x that n that I put here, if n is 1, okay, suppose n is 1, if I put n is 1 here, it will be 2. 2 is greater than 1. Okay, if this is true, so this one will be also true. Okay, just for this case, so it is done. But in case you are in doubt, just do what? Just write down. Okay, for n equal to 1, it will be 0, it will not work. But for n equal to 2, then check if n is equal to 2, when suppose for u2 and u3, just check this one must be greater than this one. Okay, just in this way, and then just check this one. Sorry, yeah, for this one, what do we have to do then? Then we have to solve. Okay, we have to solve. Now that we know that un plus 1 is, okay, is always greater than un, okay, what we have to do, the second step it is just to find the limit. Okay, find the limit of this, of the absolute function. The absolute is 1 upon ln. Okay, what will be the limit? Limit must be 0. If it is not 0, then you have to show or test fail. Okay, if it is not 0, like 1, 2, 3, so it is divergent. If it is 0, it's convergent. But if it is in not a number, like it is infinite or something like this, so it will not, test there will fail. 1 upon this guy, you get 1 upon infinite, and this will be 0. So by this one we can say that this is 0. Okay, the limit of un, okay, of the absolute value for this guy is 0, and the function is decreasing. So by Leibniz test, okay, by Leibniz test, we can say that this series is convergent. Okay, yeah. If you are in doubt about just to check this one, just go and use directly this, how can I say, use directly this one. Even you can just keep this one here and call him back. Call this one here, just if you feel like ln plus 1 minus ln, okay, and keep it like it is greater than 0. Then solve for this, we'll get ln plus 1 upon n. Okay, this will be also always greater than 0. If you check this one, this is always greater than 0. This will never be lower than 0. What does it mean? It means that this is true. Okay, yeah, just like this. Thank you, bye.